Welcome everyone. Thank you very much for joining my talk here and providing me the opportunity to show what I'm researching on in the group of Professor Jasmin and Aghassi-Hagmann at the KIT Institute of Nanotechnology. And today I want to give a talk about inkjet-printed array that can realize a physically unclonable function which can provide unique identifiers in novel printed and hybrid systems. So let's first start off with printed electronics. So one of the big reasons we are all here, giving some points about the technology. So what can it provide? Provides large area of fabrication on various types of substrates, rigid, flexible, while flexible being the go-to goal. And it can, with these new form factors, provide novel applications in various forms. And to give a qualitative overview against classical CMOS-based devices with printed active devices, we have a little table here where we just compare the performance parameters in a qualitative way. And if we compare both technologies, we can see that especially in the performance region, meaning operating frequencies, integration densities, printed electronics cannot really cope with classical silicon-based electronics, but that is also not always required. So operating frequency integration densities way higher in silicon-based electronics, but the interesting thing comes about the form factor. So here silicon-based electronics is tiny and it's on rigid substrates, usually partially flexible when thinned back. And printed electronics allows for large area flexible substrate manufacturing. An especially interesting printing technology is classical inkjet printing, which is a non-impact print method. On the right-hand side, you can see exemplarily Fujifilm Dematics. Probably many of you know this device for rapid prototyping. So inkjet printing, here the benefits are pretty clear. The fluid is directly ejected from the nozzle on the substrate. There is no contact required between a cliché and the substrate. Layouts are adaptable in software, so adaptability is very high. It's a precise, mechanically precise technology. This device here can achieve step sizes of 5 micrometers, and the material waste is very low, which can provide a sustainable fabrication method in the future. And here we can see, for example, how a droplet is ejected from a printed nozzle. And droplet sizes vary. In our case, it's 1 picoliter up to 10 picoliters per droplet. So as we already have seen that the differences between silicon-based electronics and printed electronic active devices is pretty stark. But what now can be provided by merging both technologies are so-called hybrid systems, where we utilize the high-performance information processing and signal transmission and communication of classical integrated circuits, combine it with large area printed conductive wires, in this case, on stretchable substrate for near body sensor monitoring. Or here you see a foil with printed silver interconnects and classical LEDs. So there are many novel possibilities. And here also novel supply chains emerge. And in that case, we also have to think about the security of those devices if we want to employ them, for example, in the IoT. And to provide security from the hardware basis already, one solution or one approach is to provide a unique identifiers for these novel hybrid systems. This can then show the device authenticity and always provides a unique device or system fingerprint. So how can that be realized? This can be, on the one hand, realized by classical memory, say in read-only memories or EEPROMs, but another possibility are physically unclonable functions. So the main difference between classical storage memories and physically unclonable functions is that the bits or the unique ID is generated in a non-volatile fashion, while the unique ID on a ROM or EEPROM is usually stored inside, which makes it really susceptible to outside attacks. And to describe what a physically unclonable function is, there's this really nice a quote by Mr. Sophie, which I'm going to read out because it describes it pretty densely and perfectly. So physical or physically unclonable function is a function that outputs a device-specific response by extracting its intrinsic physical characteristics. And what does that mean? So in our case, to generate a unique ID, we will utilize the inherent intrinsic variability of all kinds of materials. In our case, it's printed transistors to generate these highly unique IDs. Possible application scenarios are in identification, authentication, and encryption. And my talk and what we are doing is more focused on identification purposes. The requirements for a system to be classified as a PUF is that it has to show this challenge response mechanism. Now, to quickly introduce you to this challenge response mechanism, you can see on the right-hand side we have 4 ICs which all have the same internal circuitry. They're all manufactured identically. Now you stimulate the system with a so-called challenge, where you just apply, say, some kind of a bit string to the system, address something. The challenge is always the same, but due to the intrinsic variation of the full system and the devices incorporated in the system, each response differs. And this generates a unique identifier, and only when you apply this challenge. So if you remove supply voltage, you cannot read anything from this system. So this is the beneficial approach using this thing. Now, what we do is we utilize printed electronics, as printed electronics usually suffers from increased variation when compared to classical CMOS-based technologies, and exploit this kind of bug as a feature to generate highly unique IDs. So the standalone component that we utilize are inverters. So you can see one layouted on the right-hand side. We will incorporate them in an array structure that we will address systematically, which I will then also show. And if the basic relationship that you have in an inverter, you will measure some output voltage based on the applied input voltage, which generates a current in the device, and variation in the drain current as well as the resistor will lead to a output voltage which differs for each inverter. The devices that we utilize are electrolyte gated transistors. Here the signal routing layer consists of indium tin oxide, the semiconductor is indium oxide. As isolator, we use a composite solid polymer electrolyte to operate the devices at very low voltages, around 1 volt, and as top gate we use P.PSS. So from the schematic architecture, as said, what we want is an integrated design. So at the end, we want to have a standardized interface of our circuit that can be interfaced to further follow-up stages. So how does it look like? We decided to integrate our inverters in an integrable design with a common VIN, VDD, and ground lines. And what we need is also access to the output voltages. The output terminals, however, have to be routed over the VDD line, and therefore we need crossovers, which provides another level of challenge when you utilize novel devices and you have a fully interconnected system with novel devices, because therefore we sometimes cannot utilize the high performance materials that we have in classical manufacturing, and we have to a certain degree cope with what we have. So how is the so-called response generated based on the challenge? So the setup is pretty straightforward. We now have multiple inverters here, 0 to m-1. And what we will do is we apply the input voltage to the common gate line. All inverters will start conducting current, output voltages will drop. And what we now do is a permutation-based addressing of always 2 inverters that you can see here, inverter number 0 with inverter number 1. We forward both output voltages via the so-called sub-challenge by addressing multiplexers to a comparator input that we use as a decision threshold to generate the sub-response. So this is how 1 bit is generated. We iterate over this thing of multiple steps to generate the full response. This allows us to generate responses in a differential fashion. So we don't really care about wandering VDD or some influences in the ripple in the VDD or ground lines. And the maximum response that we can generate using this method is n times n-1 divided by 2 bits. This architecture can be classified as analog weak paths, so there are distinguishings, which I'm not going to talk here in that case. And as said, the design is integrable. What we decided on was incorporating 9 inverters, which leads to a 36-bit wide response. So here you can see the array fabricated. And as already mentioned, we use electrolyte gated transistors and these indium tin oxide-based thin film resistors. We use inkjet printing technology and laser ablation to structure the system. So what you can see here, this light bluish lines, is the indium tin oxide, while the rest also quite transparent. Difficult to see other inkjet printed devices, which where the semiconductor isolator, gate metallization, and the crossover stack is fully inkjet printed. And what we also have is a standardized interface, so we can use this chip and place it into another system to provide this unique identifier, which we generate from these printed devices. From the architecture, we had to do a little bit of a special thing due to the high sheet resistance of, say, ITO. So what we have here is a VDD line, which, of course, the resistivity increases at increasing distances, which would then lead to the inverter, which is the farthest away from the VDD line, to have the lowest output voltage in a systematical fashion, which is what we don't want, because we want at average a zero value with some kind of deviation around it. Furthermore, we also have the ground line where the current is returned. So what we did to mitigate this issue and dropping output voltages at increased VDD lines is to route the ground line at the same direction. Now, what this leads to a source degeneration in the devices that are furthest away, because you have a source resistance at the source terminal. And this kind of balances out this very systematical error, which would have been even doubled if you would have routed the ground line to the other side. Furthermore, another challenge is to print the common gate line, as PSS doesn't have the electrical conductivity as classic metals. So we use 2 input terminals to distribute the voltages pretty well. Yeah, here you can see the output characteristics at a supply voltage of 1 volt. We measured the transfer curves of the output voltages, and you can see they're fully functional. We have this system supply current, which rises at increasing input voltage, and the gate leakage to confirm that our devices do not show shortcuts. Now, to generate a response, which we now did in software, with the mechanism that I showed before, we were able to generate a 36-bit wide response at a VN voltage of 0.5 volt. But what you can also do, as you have seen, our inverter curves show a crossing behavior, which is very interesting, so a very nonlinear behavior, is to exploit and increase the challenge response space by incorporating multiple input voltages instead of 1. So now you can generate 2 times 36-bit wide responses without changing the hardware, which adds, as said, another challenge in printed electronics especially. So here we were able to generate 2 36-bit wide responses with 2 different input voltages, and the Hamming distance between both of them is 7, which is not super high. So here we have to look into how to increase this value further to make the responses more distinguishable, because if they're really close to each other, this reduces information entropy. So, and that's it from my side. I thank you very much for your attention. And if there are any questions, I'm here. Thank you very much.